Ever wondered how your computer actually understands the code you write? Or how programs run at the lowest level, interacting directly with the hardware? You're in the right place. Welcome to Whiteboard Doodles, the channel where we simplify tech-related concepts using whiteboard animations. Today, we'll explore assembly language, the essential building block for how computers execute instructions at the hardware level. Let's get started. First, let's take a look at what assembly is. Assembly language is a low-level programming language that acts as a crucial bridge between the code we write and the machine code that a computer's hardware understands. Unlike high-level languages like Python or Java, which are designed to be easier for humans to read and write, assembly language is much closer to the computer's hardware. This gives programmers direct control over the CPU and memory, allowing them to optimize how the machine performs tasks. Each instruction in assembly tells the computer to perform a very specific operation, like moving data between registers, performing arithmetic, or jumping to a new instruction. Because of its precision, assembly is used in areas where performance and control are critical, such as in embedded systems, game consoles, device drivers, and even operating systems. Though it can be more challenging to learn, understanding assembly gives you a deeper insight into how computers really work at their core. Now, let's take a look at the basic components of assembly. The basic components of assembly language are the building blocks that allow you to communicate directly with the computer's hardware. These include instructions, which tell the computer what action to perform, and operands, which specify the data the instruction will work on. Assembly uses mnemonics, that is, human-readable abbreviations like move, add, or jump, to represent these instructions. Each instruction operates on registers, which are small, fast storage areas inside the CPU where data is temporarily held during operations. It's important to note that assembly syntax depends on the architecture of the device you're programming, which means that code written for one type of CPU, like x86, won't work for another, such as ARM. Together, these components give programmers fine-tuned control over how the computer handles tasks, allowing for efficient and precise execution. Next, let's take a closer look at the CPU registers. CPU registers are small, high-speed storage locations within the processor that hold data and instructions temporarily during computation. They play a crucial role in the execution of programs, as they provide the fastest means for the CPU to access and manipulate data. There are different kinds of registers, each designed for specific purposes, such as general-purpose registers, which can hold data for various operations, special-purpose registers, like the instruction register, which holds the current instruction being executed, and the program counter, which keeps track of the address of the next instruction, and status registers, which maintain information about the current state of the CPU, including flags for arithmetic operations. For example, consider a simple operation where you want to add two numbers. The CPU might first load the first number into a general-purpose register, let's say register A, and the second number into another general-purpose register, register B. The addition operation is then performed using these registers, with the result stored in a third register, register C. This use of registers allows the CPU to perform calculations rapidly, significantly enhancing overall performance. Now, let's briefly discuss flags in assembly. Flags are special bits in the CPU that store the results of operations and help control the flow of a program. These status flags are updated automatically based on the outcome of instructions and are used to make decisions during execution. For example, the 0 flag is set when the result of an operation is 0, while the carry flag is set if an arithmetic operation produces a result too large for the register to hold. The overflow flag tracks whether an arithmetic operation results in an overflow, and the sign flag indicates whether the result is negative. Flags are especially important in conditional operations. For instance, after a comparison, a jump instruction will check the status of these flags to determine whether or not to jump to another part of the code. Understanding flags is key to controlling how the CPU processes tasks and reacts to different outcomes in assembly programming. Now, let's discuss memory and addressing modes. Memory and addressing modes are key concepts in assembly language that help us understand how data is stored and accessed in a computer's memory. Memory refers to the physical locations where data is kept, allowing programs to retrieve and manipulate information. Addressing modes define the different ways we can access this memory, determining how the CPU interprets the addresses and instructions. Common addressing modes include immediate addressing, direct addressing, and indirect addressing. For example, in immediate addressing, you might use an instruction like add R1, 5, which adds the value 5 directly to register R1. In direct addressing, the instruction could be add R1 at 1000, where 1000 is the memory address containing the value to be added to R1. Lastly, in indirect addressing, you might see add R1, R2, where register R2 holds the address of the value to be added to R1. This demonstrates how addressing modes help us efficiently access and manage data in memory while programming. Next, let's take a look at the basic assembly instructions. Basic assembly instructions fall into several categories, each serving a unique function in programming. Arithmetic instructions perform mathematical operations. Add R1 R2 adds the value in register R2 to R1, while subtract R1 R2 subtracts R2 from R1. The multiply and divide instructions perform multiplication and division respectively. Logic instructions handle bitwise operations. End R1 R2 performs a bitwise end, where only bits that are 1 in both R1 and R2 remain 1. Or R1 R2 performs a bitwise OR, setting bits to 1 if either register has a 1. Exclusive OR R1 R2 performs an exclusive OR, resulting in 1 if the bits differ. The NOT instruction alternates the bits in a register, changing 1s to 0s and vice versa. Control instructions direct program flow. Jump label causes the program to jump to a specific point labeled in the code, and compare R1 R2 compares the values in R1 and R2. Based on this comparison, jump if equal jumps if the values are equal, while jump if not equal jumps if they are not. Data movement instructions transfer data. Move R1 R2 moves data from R2 to R1. Push R1 saves R1's value onto the stack, and pop R1 retrieves the last value from the stack. Finally, bit manipulation instructions include shift left, which shifts registers bits left, essentially multiplying the value by 2, and shift right, which shifts right, dividing the value by 2. Rotate left and rotate right rotate bits left or right, looping them back around. These instructions allow precise control over data, arithmetic, and program flow in assembly programming. Keep in mind that there are even more instructions available in assembly, providing further capabilities for developers. Now, let's take a look at how assembly is executed. Assembly language is executed through a process known as the fetch-decode-execute cycle, which is fundamental to how a CPU operates. This cycle consists of 3 main stages: fetching, decoding, and executing instructions. During the fetch phase, the CPU retrieves an instruction from memory, typically pointed to by the program counter. For instance, if the instruction is shift left or 1, the CPU fetches this command from memory. In the decode phase, the CPU interprets the fetched instruction, determining what action is required and identifying the involved operands, such as recognizing that it needs to shift the bits in R1 to the left by 1 position. Finally, in the execute phase, the CPU carries out the operation as specified by the instruction. In our example, it shifts the bits of R1 left, effectively multiplying the value by 2. This cycle repeats for each instruction in the program, allowing the CPU to process commands sequentially, whether they involve arithmetic calculations, logical operations, or control instructions. By understanding this cycle, we see how assembly language directly translates into actions performed by the computer's hardware, connecting human-readable code to machine-level execution. Now that we've learned about the basic instructions and how they are executed, let's take a look at a practical code example. In this assembly code example, we start by loading the values 5 and 10 into registers R1 and R2 respectively. The add instruction then combines these two values and stores the result in register R3. To determine whether the result is even or odd, we perform a bitwise AND operation with 1 and store the outcome in R4. The AND operation effectively checks the least significant bit of the sum. If it's 0, the number is even. If it's 1, the number is odd. Initially, we assume the result is odd by loading this string into register R5. We then compare R4 to 0. If they are equal, it indicates that the sum is even, and the program jumps to the even number label to update R5 with the string even. If the sum is odd, the program skips this step and jumps directly to the end label. This example effectively demonstrates basic arithmetic operations and conditional checks in assembly language. Now let's briefly take a look at some real-world applications of assembly. Assembly language may seem low-level compared to modern programming languages, but it plays a vital role in many real-world applications where performance and precise control over hardware are crucial. For example, it is commonly used in embedded systems, like those found in cars, medical devices, and household appliances, where efficiency and direct control over hardware resources are essential. Game consoles and graphics programming also utilize assembly for optimizing performance and making the most out of hardware capabilities. Additionally, assembly is critical in device drivers, which act as the interface between hardware and the operating system. Even parts of operating systems themselves, especially those that need to interact directly with hardware, are often written in assembly. By using assembly language, developers can fine-tune programs to run as efficiently as possible, which is particularly important in resource-constrained environments or performance-critical tasks. Lastly, let's discuss the limitations of assembly. While assembly language offers significant advantages in terms of performance and control over hardware, it also comes with notable limitations. One major drawback is its complexity and verbosity. Writing code in assembly requires a deep understanding of the underlying hardware architecture, which can be daunting for many programmers. This complexity leads to longer development times, as even simple tasks can require extensive lines of code compared to high-level languages. Additionally, assembly is not portable. Code written for one architecture typically cannot run on another without significant modifications. This lack of portability makes assembly less suitable for large-scale software development, where flexibility and maintainability are essential. Furthermore, assembly lacks the rich libraries and built-in features available in high-level languages, limiting its use in modern software applications. Overall, while assembly is powerful for specific tasks, its limitations can hinder productivity and adaptability in the fast-paced world of software development. In conclusion, assembly language serves as a crucial tool for programmers who need precise control over hardware and require optimal performance in their applications. While it offers significant advantages, such as speed and direct interaction with the CPU, it also presents challenges like complexity, lack of portability, and reduced flexibility for large-scale software development. Understanding these aspects helps developers make informed decisions about when and how to utilize assembly, ensuring they leverage its strengths while being mindful of its limitations. This concludes our exploration of the basics of assembly. If you enjoyed it, consider subscribing to our channel and liking the video. Feel free to also check out our other videos on related topics. Thank you for watching.